that fine? Okay. I can take this off, I was told. Okay, hi. Sorry for not being here at the allotted time. It took us 1.5 hours to get here to do 20 kilometers. Yes, so I'll give you a quick whirlwind tour of where we are with HDF5 at ESRF, and give you also a little bit insight what we call the EBS. So just what I'm going to present is how EDF has become central, HDF has become central to the ESRF data strategy. Yes. So for those of you who don't know where this beautiful machine is, it's only 3 hours drive up here, if there are no traffic jams, up the valley, and you can see it in the middle of this picture at the foothills of the French Alps. And if you go closer, you'll see that there's a number of facilities there which are also using HDF5, like ILL, which is a neutron source. There's the European, one of the outstations of the European Molecular Biology Lab, and the French Structural Biology Lab. Yeah. Our mission, just so that you, because you'll be hearing a few talks from ESRF, is just a quick overview, is we basically a user facility. We provide photons, and then scientists who have ideas and samples to measure propose to measure these, and they come there to ESRF, and this is all paid for free of charge, as long as it's peer reviewed. You can also buy beam time. And one of the new things is that the data that we're producing is now open data, so that we guarantee that everyone can have access to this data. We also have a challenge in terms of data management, say, or data formats, is it's very heterogeneous. So these are the main categories according to which we classify the different experiments that people do there. But it's very varied, from life sciences to paleontology to engineering to all sorts of different, to quantum dots. So we have to deal with a large number of applications then. And the EBS is basically this what is called this magnet structure. 3 years ago, we replaced the accelerator that we had for 20 years or 30 years and put a new one in. And the magnets, if you look there, well, the father of this magnetic structure is standing there, Pantaleo, and the magnets are much closer together and allow you to get 100 times more flux on the samples and more than 100 times more coherent beam as well. So if you look, this is one of our flagship beam lines. We have 45 at least beam lines. One of our flagship beam lines called BM18, with the beam just going through the air and then ionizing the air. And the kind of
Andy,
data that we produce,
Andy,
yes?
We don't see remote. We don't see the presentation.
Okay, so that's a pity. What do we have to do? Maybe with Teams. No, you should go to my Teams. Okay, let's see, I'll put it in presentation mode again. Do you see it? Let me know when you see it. Yeah.
No, I think it's okay. There is one IT guy who's taking care of it. Because it's
Yeah, he's actually on the screen. Yeah, he's on the screen.
Okay. Yes,
we see it.
now we see it.
Okay. So I just whip through the slides that you didn't see, the pretty pictures, so this is the new machine, and this is a nice beam that it gives. So the data it gives, we have lots, as I said, there are lots of different kinds of data, but one of the most exciting bits of data is this called the Human Organ Atlas, where we actually had down to from the macroscopic level down to the cellular level, we are imaging all of the human organs. So this is just one experiment out of hundreds, but this experiment has had quite a lot of publicity because of, oh wait, I wanted to actually show this movie. This movie is, how do I show this movie? Let's see. Oh yeah, yeah. So this movie you can also go and have a look, which is on the Human Organ Atlas website, but you can see how the resolution of this goes down to just 1 or 2 microns, which gets down to the cell level. And if we move along there, you'll see that we can actually see the neuron structures as well, yeah. So this is something which is also making a lot of interest because it's bringing medical staff into using the data, and this data will be kept forever because it's something like it's an atlas of all the human organs and also of different pathologies as well. So you can see, yeah, as we get down to the level of very fine structures. What I don't know, this actually brings up a challenge for HDF5. I don't know how this is managed. The moment is you got different resolutions. So you got this global view, and then certain parts of the data are at a very high resolution, but not the entire data set, because that would just be enormous. Yeah. So certain parts have actually been made like that. I don't know, maybe you can explain to us how we can store that multiple resolution data, yeah. And it's also been used for COVID. So this is a picture of a human lung, which has been nicely colored, of a patient who passed away of COVID, was judged as one of the best pictures of 2021 by National Geographic. And you can see the kind of data that allows you to then study at a quantitative level what happened to the patient, because the good part of your lung is the one that has all the little alveoles you can see, and the bad part was this is when the COVID got into the lung and destroyed the lung. Yeah. So that gives you just an idea of some of the kind of data we produce. We can actually classify it as raw data, which is basically 1 and 2D, and then we get process data, which goes into 3D. With the EBS, we've chosen HDF5 as our preferred format. This is, and I'll explain a little bit what that means. Users get a lot of services now from the EBS, which we didn't have previously, in terms of richer metadata, the curation of data, the services that allow you to use that data are downloaded. You don't have to keep it on your floppy disk or on your hard drive. And when it goes out into becoming open, this data is then the same services are available to all the users. One thing we haven't optimized yet is the access for machines. Yeah? But this, I think, is something which will be like the next stage, is how to give machines easier access to this. And you can, this is the data that's been curated since, I think, 2015, 7 petabytes of raw data. And this is only like half, it's less than half of the amount of data actually produced. So we don't curate everything. At the moment, we curate a minimum of process data and as much raw data as we can. And all our data is accessed via catalog. So the same data set you saw over there is stored in this catalog, where you can then, this is where the machine access could actually be made optimized. Yeah. So I just wanted to show you in this graph here where we all use HDF5. So we use it during the data acquisition in our new control system called Bliss, in the 2D detector system called Lima, where you'll hear the talk by Sam later today. We use it when we archive the data via the portal. You'll hear the talk by Loic. And there's a talk also by Thomas when we start reducing the data, compressing it, but also calibrating it, reducing it. And finally, with the data processing, we also store it in HDF5. So you can see it's really become central to the way we handle data. This doesn't mean it's the only format, but it is our preferred format. We use it as much as possible. And I thought it's useful just to say why we chose this. So when I was writing the slide, it reminded me of the joke about why did the chicken cross the road, yeah? I'm sure you know the answer, but if you don't, we can tell you. Well, it was really because there were some very obvious reasons. We were coming from a background where we had files with 1 image per file, and we produced millions, billions of images. So this was obviously not scaling well with the file systems. Yeah. Then we have a community standard called Nexus, which you'll probably hear in other talks, this is defined for HDF5. So we wanted to make sure that we could use this community standard. Compression is very important. So we got many data sets can be highly compressed because we have very little. Few photons in them. Yeah. So you can have lots of zeros. We wanted to integrate with the detector companies because in 2020 we bought 10 large detectors from this company called Dectris, and they were producing HDF5. We wanted to mix everything. A standard API was also one of our very strong requirements. Before we moved to HDF5, a standard API, we had a home-brewing system where everyone had their own version of the API. And this was a nightmare because you couldn't actually call it a standard anymore then, yeah. Then we needed efficient writing and reading. And finally, I mean, you can't produce petabytes just by using ASCII, I think, yeah. And we need the long-term support, yeah. So I won't spend time on these following slides, just to give you a very quick overview. Our data acquisition produces in-memory to the scan data, which is actually reading out the 0 and 1D detectors, and the 2D detectors go through a Lima system, which will be described later. And then we persist this using VDS. So our file structure looks like this. This is very nice to have the VDS and to have soft links and that. This makes things very easy to manage. So we can have parallel writers. And the format is the ontology or the keywords we use are from the Nexus community. And you can see how things look like this. You can look at files like this. Maybe this slide is worth spending a few seconds on. What we use is just standard HDF5. So we haven't moved to HSDS or other tools, but maybe we should when I was listening to the talk previously, because you'll see our main problem is still concurrency. So maybe we can find some solutions there. And we don't use Swimmer, the first version of Swimmer. We might use the second version of Swimmer. The main problem with our use of Swimmer as it was, first of all, we didn't have a POSIX file system everywhere. We only had we had a mixture of NFS and GPFS. And finally, and then also the pattern of reading and writing can happen over a very long time. We have very different use cases. We have some experiments that produce only a few megabytes of data, very short bursts of data. Others that produce hundreds of gigabytes of data. And a scan, what we call a scan, is where we're writing to the file of what's happening in the experiment. This can last from a few seconds to hours or days. And when it's running for hours or days, and at high speed, it can be running at 20 kilohertz or something, you can't stop the writing. But the readers, because the experiment's going on for a long time, or hours, they want to evaluate and get the information to see how the experiment's advancing. So our main issue there is that at the moment we have to do workarounds to have concurrent access. And we don't have the ideal solution there. So one thing we've started working on, but we will be very keen to discuss with you, is also making the data which we have in memory, so the first slide I showed, and making that available via the same API. So the H5Pi API, which is quite well liked and quite simple, based on dictionaries and iterators, is to say that we can actually recover access the data that's been streamed through memory before it hits the disk using the same API. So this is something we're going to develop now for the rest of the year probably, which will allow us application programs with no modification will be able to open a data stream, and that will use, say, open group, search for group, get all the information, and that there'll be some delay if it's still going through memory, and if it's already left memory, it'll then switch to the it'll switch to the file. So we're trying to make this move transparent so that we can have access faster, but also in a coherent way. Yeah? Then there's a very nice talk, I think, coming up soon about H5 Web, which you'll hear about. So I won't spend time on this, but I think this has been a very important development. The same as one of the tools developed by also one of the people here, Thomas, and a team called Silks. has been widely used for in the photon-neutron community for looking at HDF5. Yeah. So this is a PyQt, Python Qt application, but very widely used because it understands the Nexus ontology. And this is actually also a very interesting data set where we are getting data for a new experiment called serocrystallography at 8 gigabytes a second coming off, and we can't write that to disk, so we have to compress it in a very drastic way. So the data basically looks of lots of spots on a background, and the way we do it is in real time, we average the background and then find all the spots using highly optimized GPU code so that we can reduce the data down to a factor of 100 and store only, and if you look at, it's a bit hard to see there, but there's actually the program which allow you to regenerate the data, as well as the list of spots, as well as a formula describing the background. So we're using HDF5 like that, and I think there's a talk also about code embedded in HDF5 now. So we're already doing this, and this allows us then to go under 1 gigabyte a second, which we can then write to disk. Yeah. I won't say anything about Nexus. The other thing that's also getting very, because I mean, Nexus is our standard dictionary of standard tags, and I think you'll also talk a bit about Nexus, Shando. It's all up there, but it really saves us a lot of time because we don't have to start from scratch for the basic things. Yeah. But it's a 20-year-old effort, yeah, and only now has it really been adopted, I'd say, more widely. Yeah. Then the other thing is we're working a lot on workflows to move from to automate the data reduction. Yeah, so we have GUIs, we have the control system. People have their own scripts, notebooks, and so on. And what we're trying to do is to formalize or make, in a way, first of all, automate and make it reproducible how the data are reduced. The data are reduced, and for that we're using workflows. So the workflows, we have avoided developing yet another workflow engine. We use existing workflow engines, but we've standardized and abstracted the description of the workflow and the encapsulation of how to run it. So to automate it, the workflows are triggered by a client, who can be a command line client or can be a graphical client, goes into a job scheduler, a standard one called Celery, and then Celery either runs the job as locally, if it's a smaller job, on the local computer, or it can distribute it to Dask or to Slurm. We have a Slurm cluster as well. And the results are persisted in HDF5 and then come back. So this is an area where we've been very active over the last year, and you can check out the system over here. There's also a web interface being developed for this as well. I thought to wrap up a final word about what we're doing on the European scale as well. So we're part of this community called the PAN community, Photon and Neutron community, where they are represented by two organizations now called LEAPS, the League of Accelerator-Based Photon Sources, obviously, the name is obvious, and LENS, which is a League of European Neutron Sources. You see how they spread around Europe. You can get an idea of the amount of data, the ones that we know about, what the data production rate is at these different sources. So the winner is obviously XFEL at 100 petabytes a year, and these data are, they actually right now, XFEL is having their review committee where they're talking about how they're going to move more data into HDF5. Yeah. So in the case of ESRF, we predict when we at cruising speed, once the new machine is brand new, yeah, it's only since August 2020. When we're at cruising speed and all the experiments are working at full speed, we predict 50 petabytes a year. At the moment, we're more like under 10, yeah. And what we're doing, and this is something which is also I also try and do because sometimes I'm involved in these projects, is to use these European projects where we get funding to develop and further enhance the tools around HDF5. So some of the tools you'll hear about here were developed under using funding from European projects, and others, for instance, one very important aspect is a lot of people depend on H5Pi. And if you look at the latest, the last commits, most of them have been done by Thomas Kluwer, and Thomas Kluwer is paid for by the Panos project. for instance. So we try, I mean, we encourage everyone to put their money back there into these tools, but there is scope to do more, I think. And I'm hoping that via the European Open Science Cloud, we could actually get some funding for this, yeah. Because one of the things we're going to do in the European Open Science Cloud is to push an open data portal of all open data coming from photon and neutron sources, yeah. So what are the problems? I mean, when not everything's easy sailing, of course, as you know from your own experience. When supporting HDF5, the first criticism we get sometimes is many applications don't know about HDF5. Of course, this is obvious because they were written, some of them a long time ago, and some of them were also written by people who were happy with CSV files. The most common format sometimes is just ASCII, command-separated value files. And this makes it difficult for them. And also, there's a cultural change. You have to change, and you have to get hold of the developers. They don't always have access to our scientists don't have access to the code. So this is a big discussion point often, and we try and help as much as possible. But there's no magic solution out there. You just have to work on it and stay in contact with the scientists. So we've developed also some tools which will convert to other people's formats, the formats that they use, and these conversion tools we plan to run automatically using workflows. Our main problem that we're trying to solve is multiple readers. So as I explained, this thing of having multiple readers who can come in at any time because the writer opens a file and closes it as soon as they finish the work, so that they don't block the file. But the order of the writer and reader can change at any time. Yeah? So what I'm hoping to get out of this workshop is if Swimmer 2 discuss with the developers, Swimmer 2 will solve our issues or not. If there's a more general solution and how we can share tools. I was wondering at one point if H5 Web could replace HDF5. I don't know how. You know, HDF5 has a long history as well with a lot of features in it. Is it possible to reach that point of maturity where people only use the web? But we'll hear more from Brian and from Loic and how we could actually try and increase the support for HDF5 via EU projects. And to conclude, I mean, we went from one of like the least active institute in HDF5 20 years ago in the community to now being probably one of the most active ones. And we definitely happy also that the EU projects were there to help us. And maybe, you know, there are these other formats out there, but maybe we can get more formats being supported by one format. Yeah. And our main issue is still that. Yes, and thanks to all these people, yeah, some of them are here, who have helped the adoption of making HDF5 actually happen at ESRF. It's a huge work on 47 instruments. Yeah. That's all. Okay.
Thank you, Andy. Is there any question? I don't know, remote or...
So my name is Alexander Jelinek. I'm from the HDF group, just for everyone else doesn't know me. I have a question. You talk a lot about writing concurrently to a file. Since you're obviously a large facility, have you ever thought writing to something that's not the HDF5 file as you know now, or as you recognize now?
No,
in other words, do you have to really write immediately an HDF5 file?
No, we have thought about that, and this has been a point of discussion. I see two issues with that. The one was more cultural, is that we were, because we discussed this with some scientists, what if you just made a copy of this file in parallel, which is a simple format, then I could use it. Is that, first of all, it was going to delay the move to HDF5, but okay, if you have a real problem, you have to find a solution. But secondly, having another format means another API. And this is the thing which, you know, we've seen the huge effort it requires for people to change their programs to go to H5 or to HDF5 API. And then if we came, well, now there's another API you have to use to get your data, it's going to, you know, we're just doubling the effort. So I think actually our approach of having, trying to extend H5 to read, in our case, stream data, but it could be another format now in this case, will address both these issues.
So my follow-up is basically HDF API does not have to be only HDF5 format.
Yeah.
Once you have the API, it can go other places. So that's something that I don't know how much, and I'm speaking for myself, within the company was really thought about, you know, that we get out of that thinking that HDF5 library only creates and reads HDF5 files.
Yeah.
The other thing is also, are you thinking about cloud and cloud computing? Obviously, are huge facilities, so either commercial cloud providers or something that you have on premise. Have you ever thought about those kind of things?
We've been, in the last 10 years, we've done multiple experiments with the cloud. Yeah? So the cloud would, let's say, a cloud is a solution for certain things, but the current limitations are, first of all, when you have a lot of data, getting that to the cloud fast enough. If you want real-time feedback or quasi-real-time feedback, this is something which is sort of limited by the cloud. And then secondly, I think the main problem we have is manpower. If we had more manpower, these issues could be addressed. And we've noticed when we used the cloud is that scientists, Amazon Cloud has advantages, it's extremely well documented. So sometimes it's just enough to give a scientist a login and they can do the rest on their own using the documentation. But not all scientists can do that. So then you need people to help them. Yeah. But yes, it is theoretically an option, but practically we haven't actually got, we're not getting there. Yeah. Okay.
Hey, Andy.
But maybe just to finish on that one thing I wanted to add for John is when I was listening to that, I thought one thing we could do locally is if we were using S3 or an object store, maybe concurrency could be addressed that way.
Exactly. That's what I asked is, you know, so cloud doesn't necessarily mean moving to Amazon or Azure or whatever. You can create kind of the infrastructure for a cloud in your own facility. And by that, I usually think of like object storage versus Lustre, Kubernetes versus Slurm, that sort of thing. And those decisions may have cost benefits. And furthermore, I think the parameters we're used to kind of change when you switch these things up. For example, like object storage systems usually don't have the same kind of meta pressure that POSIX file systems have, right? Just because of how they're designed. So it kind of alters maybe the things you're used to, right? I would think it's worth experimenting, at least.
Yeah, I think you're right. I mean, I think this. I know from our systems guys that S3 is for object stores are for them easier to manage than POSIX file systems. So they say, wow, not a problem to move to that. Yeah.
Yeah. Your cost per terabyte might be much less and might be easier to manage. Typically, the problem of moving to object store is that it's not compatible with your applications, right? Whereas HDFS from the ground up was built to utilize object storage, so that's not an issue, at least in that case.
Yeah, we need very guaranteed performance for the writing because we can't stop the experiment and the speed at which it's going.
Mm-hmm. Yeah, I'm sure it's quite a challenge.
My question would have been exactly on the same line. I know H5 Web. You also wanted to use it together with HSDS, but you haven't mentioned anything. Have you performed some tests, or have you tried it, or you just forgotten about it, or what's the situation?
I think it's a question for John. I know that they met all the developers, John and Axel and Loic, and you did start looking at H5 Web, John?
Yes, I did. And unfortunately, I got a bit sidetracked with some other commitments, so I hadn't had as much time to look at it as I would like. But I do agree that it's really nice to have maybe like a portal where people could see their files through H5 Web. It's just as always as a matter of finding the spare cycles to work on it.
Because indeed, H5 Web is just one application. But as you pointed out, having a kind of common interface where you can use either the HDF5 file directly or another way of storing, that would be really important.
Yeah.